break afterwards. So I would like to announce the next speaker. He's currently an associate professor at the Department of Electrical Engineering and Computer Sciences at UC Berkeley. Professor Levine is focusing on machine learning for decision-making and control, with an emphasis on deep learning and reinforcement learning algorithms. Applications of his work include autonomous robots and vehicles, as well as applications in other decision-making domains. His research includes developing algorithms for end-to-end learning of deep neural network policies that combine perception and control, scalable algorithms for inverse reinforcement learning, deep reinforcement learning algorithms, and more. He has a PhD from Stanford University, and since 2016, he is part of the Electrical Engineering and Computer Sciences Department at University of California, Berkeley. So, Professor Levine, please, the stage is yours.
Great, thank you. All right, hopefully everyone can hear me. I'll get started. I'm going to talk about safety and reinforcement learning by leveraging offline data. So, as many of you probably know, reinforcement learning can provide a very powerful framework for automating acquisition of behaviors, acquisition of skills, including safety critical skills. So we can use reinforcement learning to learn policies for things like robotic locomotion, sidewalk driving, flying quad rotors, and so on. And that's very promising because if these policies can effectively use rich sensory perception, if they can develop a rich repertoire of responses to whatever situation they might encounter, then they will be very effective in safety critical systems settings. However, on the path to these solutions, reinforcement learning algorithms need to explore. So as a little illustrative example, let's say we have this walking robot, and after 2,000 iterations, it learned to walk very reliably on this infinitely large flat plane, and it walks without falling for a very, very long time. However, during the training process, it needs to repeatedly experience failures, including catastrophic failures, so that it learns essentially not to do that. And of course, in simulation, that's fine because we're pretty happy with the final policy that we get. But if this were running on a real humanoid robot training in the real world, then all those failures on the path to successful policy would probably destroy the robot, and then it wouldn't matter how far it could walk because it would be gone. So that's basically the challenge. And if we think about safety and generalization, particularly in unseen settings, I think it's probably fair to say that in the world of supervised learning, even though the problem is not fully solved, it's much better understood. Whereas in reinforcement learning, there's some pretty major conceptual challenges. So for supervised learning systems, we kind of know that if everything works as intended, then you should get decent generalization to in-distribution inputs, meaning that when your test inputs are from the same distribution as your training inputs, essentially your validation error kind of reflects what you expect to happen. But supervised learning systems may perform unpredictably on out-of-distribution inputs. So they're reliable for in-distribution, unreliable out-of-distribution. And even though the problem is far from solved, it's not nearly as bad as RL because we know that as long as we can avoid out-of-distribution inputs, for example, by carefully choosing our training set or by having some sort of uncertainty monitoring, we'll be in decent shape. So not to understate the difficulty of that problem, but it feels like something that there's at least a little bit of a handle on. When it comes to reinforcement learning, the trouble is that just acquiring a good policy already requires potentially unsafe exploration. Excuse me. So there's, in some sense, kind of no way out of that. And trying to incorporate prior data, let's say you have some prior data that tells you how to be safe. That requires you to have some distributional shift. Pardon me. Because presumably, if you're adding prior data, you want to do better than whatever happened in your prior data, which means that distributional shift is not just an undesirable artifact. It's actually an unavoidable consequence of trying to do well at the task. Okay, so pardon me. So if we can reduce the risks in RL to familiar in-distributional statistical generalization risks, like the kind in the left-hand column, then we will be much closer to methods that are actually viable for the real world. So the trouble is that in reinforcement learning, you have to have unsafe exploration. Well, you have to have some kind of exploration, which is potentially unsafe. And you have to incur at least some distributional shift, because you want to do better than whatever you've seen before. And that's basically what improvement is. But maybe there's some way to kind of get that under control and get those risks to look more similar to the risks that we're familiar with. Okay, that was a little vague. So let me try to make this a little more precise. This is the question for this talk. Can we develop data-driven RL methods? So in traditional on-policy RL, we have an RL algorithm that interacts with the world, collects a little bit of experience, improves from that experience, and then hopefully does a little bit better as a result of that. In offline reinforcement learning, where we incorporate prior data, the idea is that we take some existing prior data set, we're going to use that prior data set to train up some policy that does as well as it possibly can using only that prior data, and then we would deploy it and hopefully we would do something decent. And of course, in reality, we might still fine-tune it with additional online training after that. And one of the big promises of offline reinforcement learning, outside of all the safety stuff, is that conceivably we could take, let's say, a large data set from all the past tasks that the robot has ever solved before, use that to initialize some kind of policy that achieves some decent initial level of performance, deploy it, and that would already be way better than starting from scratch. We would avoid the bulk of that nasty exploration, like the robot, the walking robot wouldn't have to discover how to not fall, but then there would be some additional fine-tuning to really get performance up to the highest level possible. Okay, so that's kind of just offline RL in general without any kind of safety element in it. But that already gets us a lot of mileage, because if we can use prior data to overcome some of that exploration challenge, we can enable RL in many more settings. But let's talk specifically about the safe part. So we could train with offline RL, but our goal here will not just be to flat out solve a task using prior data, because that might be too ambitious in some cases. It'll be to provide an initialization for safely fine-tuning the current task, which would be done with online interaction. And there are kind of two ways that we can frame this problem statement. We can say we want task-agnostic pre-training, so use prior data to learn how to be safe in some very general sense, and then use online fine-tuning to learn a particular task. Or you could have task-specific pre-training, maybe use your prior data to figure out potential solutions for a task, and then do some very efficient and hopefully safe online fine-tuning to find which of those solutions is the best one. And then you do some online adaptation. Okay, so that's basically the idea. We're going to adapt online and explore for the new task while using something that we pre-trained from prior data to provide some kind of constraint or something to avoid those nasty failure cases. Okay, so there are two approaches to this that I'm going to cover in today's talk. The first is going to be that task-agnostic problem statement. So this is where we use prior data to learn some general purpose constraint that we will then use for some new downstream task with online exploration. And then I'm going to talk about a task-specific approach, where we would actually use data for a particular task and learn a space of potential solutions, and then select among those potential solutions with online exploration. So let's start with the first one. So here we're going to be learning a general safety constraint from prior data that is agnostic to the task, and then we can use it for online data collection for whatever task we want. So we're going to have some prior data, and that prior data can come from many different places. It could come from hand-designed policies. It could come from a previous controller that we ran on our system. It could even come from random data collection. So you can basically think of this as like whatever your system did before, somebody logged it, and that's what you're going to start with. And we're actually not going to require this prior data to actually all illustrate safe behaviors. All it's supposed to do is just provide data that illustrates how the system works. It may contain unsafe behaviors, or it might not. Now, conventionally, if you were in this situation, you might, for example, use the prior data to learn some model of your system, like a dynamics model. And then, if you want to do model-based RL, you could say, well, let's use that model to control the system. And if that's a good model, it'll work well. And then the big question you're concerned with it, is the model correct? Not is it correct on the training data distribution, but is it correct in the kinds of situations in which it will be used at test time, which will, of course, differ from the prior data because you're trying to accomplish some particular task. And that's a particularly delicate problem So coming back to that distributional shift and supervised learning comment from before, I can make this a little more concrete. You could say, well, if you trained your model using empirical risk minimization, kind of the classic supervised learning framework, then what you really did is you minimized some loss, let's say like a squared error regression loss, on your training data distribution. And then if you're asking, is your model correct? You're really asking, if I give some new input to the model, will the model make a correct prediction for that new input? And that's actually a very difficult question to answer. So one of the few things we could say is that if you evaluate the average loss under the same distribution as the one the model was trained on, and the model didn't overfit, then you would expect the average loss to be low. But in general, you wouldn't expect the loss to be low if you're testing under some new distribution, in this case, P bar of X, which might be different than P of X. So that's basically distributional shift. And distributional shift is going to happen if you don't avoid it somehow, because you're trying to solve some new task that's different from the old tasks, which means you'll probably go to different states. And in those states, they might be unfamiliar to your model. Okay, so that's essentially the problem we're trying to address. And there's something kind of funny that happened here. I went from talking about safety to talking about distributional shift. And why did I do that? That's not a very conventional way to think about things, because typically people think of safety in terms of constraints. But I think it's actually very appropriate here, because essentially, if our model is correct, then any method that uses that model would be able to predict that something unsafe might happen. So we don't, in some sense, need to do anything special for safety if we don't have distributional shift. Because in that case, your regular RL algorithm will already understand that this particular behavior is undesirable because the model is accurate. So the thing that we're really concerned about is mistakes in the model, not so much figuring out which states are safe or not. Because if the model is accurate, it can figure it out. Okay, so learned models can make mistakes when there's too much distributional shift. So one thing we could try to do is use this prior data to figure out a constraint that will avoid distributional shift. And as long as that works, then the model will be accurate, and then the model can do its own job and avoid going into unsafe situations. So can we learn constraints from prior data that prevent distributional shift? Okay, so that's what we're going to do. We're going to use prior data to acquire some object, which is going to be this distributional shift constraint. And formally, that object is going to be a function, g of s comma a, so it's a function of state and action. And that function will satisfy some property that says that as long as it's above epsilon, if you take that action, you will remain in distribution. And I'll define that more precisely in a second. And then for some downstream task, where we're actually interacting with the world, we'll only permit actions for which GSA is less than or equal to some threshold. So, and again, I just want to emphasize here that I'm using the word safe a little bit unconventionally here. I'm using it to mean guaranteed to stay in distribution, not necessarily guaranteed to like not fall or something like that. And that's under the assumption that as long as you stay in distribution, the model itself can take care of not falling down or whatever other constraint you have. Okay, so what should this constraint do? We only allow an action AT when g of SDAT is less than or equal to delta. And in particular, what we want is we want for all future time steps t prime greater than or equal to t, we want the log probability of the state in action at that time step to be greater than or equal to epsilon. Why do we want this? Well, this is more or less saying that if you take action AT, then for all the time steps in the future, you will never encounter a low probability state action. Low probability here means low probability under the training distribution. Now, this doesn't actually guarantee that you don't make mistakes, because in general, the loss is only guaranteed to be low in expectation. But in some sense, it's kind of the best we can do. So it's a little bit of an assumption that as long as the density is not too low, your probability of making a mistake will be small. Although in general, that's actually pretty hard to guarantee. So there's a little bit of an assumption being made here. But it's kind of sensible. It's saying like, you're not going to go into regions that are too unlikely, and therefore everything will be fine. Okay. So here's like a very simple straw man method we could think of for getting us started. What if we just only allow actions for which the log probability of SDAT right now is greater than or equal to epsilon? Basically, does avoiding low probability actions ensure that you avoid low probability states in the future? Because if it does, then this would give us a very, very simple method for solving this problem. Unfortunately, that doesn't really work. And the reason it doesn't really work is because in the training data, you might have multiple different actions in very similar states. So in general, you might have this fragmentation of your probability mass. So what the animation on the right is illustrating is that at that first time step, you have two actions available, up or down. And if you take the down action, it has 50% probability. All the subsequent states and actions also have that same slice of the probability mass. But if you go up, there are multiple options available to you in the data. This is in the training data, not necessarily in the entire MTP. You have multiple options available to you, and therefore your probability mass will keep on splitting and splitting and splitting, which means that even though that first time you took the up action, it had a probability of 50%, by the time you get far enough to the right, you'll have much lower probability for all the options available to you. So that's it's a little maybe counterintuitive that even though you might always take the highest probability option after that entering that top branch, nonetheless, the probability of all the options will continue to decrease. So therefore, it's not enough to simply restrict yourself to high probability actions. You need to actually consider the probability of future states and actions that you will enter after taking that action. Okay, so what we're going to do in this work is we're going to draw a connection between staying in distribution and Lyapunov stability. So many of you probably already know this, but here's like a quick 30-second primer on what Lyapunov stability is. So stability in general says that if you start at a location that is within some ball of radius delta, then for all future time, you will stay within some ball of radius epsilon. And so this is an illustration of that. So you start within the smaller dotted ball inside of radius delta. If the system is stable, you will stay within some bounded range epsilon. And for simplicity, you could also imagine that delta and epsilon are the same. So if you start within a ball, you stay within that ball. That's a simplification, but that also is a reasonable intuition. So if you have a stable system, then you can construct a Lyapunov function, v of x, such that it defines a potential field that decreases along the dynamics. So what that means is that the value of v of x should decrease as you run your system, or at least not increase. So if such a Lyapunov function exists, then it's a stable system. And I'm sweeping a lot under the rug. These are not, of course, technical statements. These are this kind of intuition. More related to what we're doing is a controlled Lyapunov function. And a controlled Lyapunov function is kind of the same idea, but for a controlled system. And a controlled Lyapunov function basically says, if such a function exists, then your controlled system can be stabilized with some controller. So in particular, it means that you will remain stable if the control U is chosen such that the dot product between the gradient of v of x with respect to x and the dynamics function f of x u for the u that you chose is negative, which basically means that v of x will not increase as you run your controller. Now, this is a lot like a value function in reinforcement learning. And in fact, the connection is more than just superficial. It can be made precise. Essentially, if formulated in a careful way, value functions can be Lyapunov functions. And the key idea that we're going to explore, of course, we don't want to stabilize our system around some epsilon ball near x equals 0. We want to stabilize it in high probability regions. So instead of using Lyapunov functions to stabilize around x equals 0, we're going to extend the concept to stabilize in regions with high density, which might no longer be a ball and might no longer be convex. So a lot of things get more complicated, but similar kind of ideas could be used. So essentially, in the same way that Lyapunov stability ensures that for all future states, the norm of x is less than epsilon, here is going to ensure that for all future time steps, the log probability at that time step is greater than or equal to epsilon. Okay, so let's come back to our safety constraint. So that's this G thing. So we're only going to allow an action when G of SDAT is less than or equal to delta. And the intuition here, and this is like somewhat informal intuition, is we're going to want to make G look a lot like the negative log probability, but we're going to make it in some informal sense a little bit like Lyapunov consistent, meaning that it will guarantee that not only is the log probability high now, but that it's going to be high in the future, which is a little bit like that property from before, where a conventional Lyapunov function guarantees that if your norm is low now, it'll be low in the future. So we call this thing a Lyapunov density model because it combines ideas from density modeling, namely that it's going to look a little bit like log P, with ideas from Lyapunov functions, which is its ability to stabilize in some region. So this is the definition of a Lyapunov density model. So it's defined as this function g, where if you take actions for which g is less than or equal to delta, then for all future time steps, your log probability greater than or equal to epsilon. For any controller, as long as it obeys this constraint. So you're assuming that you will continue to obey the constraint in the future. Okay, now there are a number of important questions we could ask about these LDMs. First, can we actually learn them from offline data? So we got on this whole track because we wanted to learn safety constraints from data. Can we actually learn LDMs? Can we guarantee that using LDMs as constraints actually guarantees bounded distributional shift? Especially under realistic conditions when you have sampling error, approximation error, and so on. And can we use LDMs in conjunction with downstream methods like model-based RL? So the answer to the first question is yes. And in fact, the algorithm that we get out of it ends up looking a lot like more conventional offline reinforcement learning methods based on value functions. For the second question, the answer is yes. And we can even account for sampling error when we do this analysis. And for the third question, the answer is yes. And we can actually show empirically that using LDMs with model-based RL leads to a reduction in catastrophic failure rates. So let's start with how we can learn LDMs from data. So I can take this condition, that basically the definition of the LDM, and I could write it down symbolically here in this equation. So what I want is to satisfy the condition that G for some state in action, which without loss of generality, I'll write at time step 0, so G of S0, A0, should be the minimum over all the actions of the maximum over all future time steps of the negative log probability. So it's essentially the least probable thing that you will see in the future as long as you act to avoid the least probable thing. That's basically what it is. And one of the things we can do with this equation is we can express it recursively. So the expression here is maybe a little cryptic, but if we express it recursively, I think it actually becomes more intuitive. So we could say that G is the maximum over negative log P now, and G in the future, where we're going to take the best action to maximize log P. So the signs are maybe are a little confusing because to sort of use a convention consistent with control theory, we're going to keep G low, but we want to keep log P high, so it's negative log P, right? So we want to keep negative log P low. So what this expression basically says is take the maximum over the current negative log P and the future negative log P, and the future negative log P is captured by G at the next time step, where the way you got to the next time step was by taking the best possible action. And those of you that are familiar with reinforcement learning would recognize this as being quite similar to a Bellman backup, right? So Bellman backup is also a recursion over time where you have something like a current reward and a future value. Here, instead of adding the current reward to the future value, we're taking a max. So we're taking the larger of the two because we're concerned with the largest value of negative log P that you will see for all time steps rather than the cumulative sum. But because it looks so much like a Bellman backup, we can actually train it with an objective that looks like a value function learning objective. And there's a small typo here that should be squared, but essentially the loss function you can use is just the difference between the left-hand side and the right-hand side of this equation squared. And that would be a valid way of training a function approximator to represent the Lyapunov density model. So our algorithm will essentially be based on this. So the LDM training procedure, just to summarize at a high level, will be first, train a density model, train a model of P on all of your prior data. 2, train this G, and I use a subscript phi now to denote that G now is a function approximator with parameters phi, such as a neural network, for example. So train G phi using any offline RL method. We're going to use a variant of conservative Q learning, but any good offline RL method will do the job. And the core of that method will be this modified Bellman backup. So the rest of the offline RL algorithm works exactly the same as any other offline RL algorithm, except the Bellman backup, instead of having a sum of a reward to the next value, has this max. And that's really the only modification. Okay, so that's how we train LDMs. Now let's talk about how they might be used. So our LDM now is going to be this function approximator, basically a neural network that takes in S and A and outputs a real number. And maybe we're going to be doing model-based RL. That's not the only way to use LDMs, but one of the ways we can use them is with model-based RL, in which case we have a learned model, FSA, which takes in SA and predicts the next state. So we're going to use our prior data, use it to learn a safety constraint, also use it to learn a model, and then try to perform the downstream task by, for example, doing model predictive control with that model, using the safety constraint to constrain the actions that we allow ourselves to take. So we only allow actions A when GSA is less than or equal to delta. So we can write this, for example, as in the form that's maybe more familiar for model predictive control. Every time step, we're going to plan a sequence of actions, A1 through H, for some horizon H, to maximize the rewards, subject to the constraint produced by our dynamics, meaning the next state is f of STAT. And then we have this additional constraint that G5 STAT should always be less than or equal to some constant. Okay. And what we're going to compare this to is an approach where instead of using the LDM, we'll just use the density model. So in some sense, kind of that's sort of the default thing based on what exists today, just only allow high probability actions. And the question that we're going to be interested in answering is, if we use the LDM to constrain our actions instead of using a density model, will we actually do better? Okay, now I just want to emphasize that this is not the only way to use LDMs, but it does provide a reasonable default way to use them with model-based RL that we can analyze to just get a sense of whether the LDMs are doing a good job of satisfying those constraints. Okay, so we're going to compare the LDM to this kind of density constraint, first theoretically and then empirically. So let's talk about the theoretical stuff. For the density constraint, we can construct a counterexample where this method is arbitrarily bad. And that counterexample is basically the branching scenario from before. Essentially, you can construct scenarios where in some states, all the actions have equal probability, but some of them lead to branches where reduction in probability is unavoidable. And in those cases, you can basically get this thing to blow up exponentially fast. So the full counterexample is described in the paper, but basically the short version is, if you just use the density as a constraint, there are counterexample data distributions that are arbitrarily bad for this. Arbitrarily bad in the sense that your constraint will be violated, and it'll be violated very quickly. The guarantee provided by LDMs is essentially that if you pick a constant C, then even in the presence of approximation error and sampling error, your future probabilities will be lower bounded by some expression. Now, because you're incurring error, they are not actually lower bounded by log C anymore. Like if you had a perfect LDM, they would be lower bounded by log C. But if you have an imperfect LDM, they'll be lower bounded by log C minus some error terms. But critically, all those error terms can be made small if you have low enough approximation error and enough data. So let me just walk through what those error terms are. So epsilon p, this is your error in fitting the density model. Essentially, you're going to use some kind of density model to train the LDM, and that density model is attempting to estimate the distribution in the training set, and that estimate itself might be wrong. So if it's wrong, you incur some error. But hopefully that error will be small. This constant r essentially represents recoverability. So it's a constant describing how easy it is to come back from low density regions. If you live in kind of an environment where you fall off cliffs a lot, then of course this value will be bad. This k is the full task horizon, or if you're in discounted setting, it would be 1 over 1 minus gamma. And this epsilon ls is the TD learning error per iteration. So when you're doing this temporal difference learning, the Bellman backups, you incur some error, and that error is epsilon ls. And that's kind of the main source of error that you're worried about when training the LDM. And epsilon fin, this is the error in fitting the density at the last time step, very similar to epsilon p. So the thing to note about this bound is that everything is basically multiplied by some kind of epsilon. So if your error in fitting the density model is low and your error in the TD backups is low, then this quantity as a whole will be low. And some more things you can note about it is that it increases with horizon and it increases with this recoverability constant. Okay, let's talk about some empirical results. So here we're going to be testing the LDM with this model-based method. So this is model predictive control with a learned model and the LDM as a constraint on a hopper control task. So this is a one-legged hopper that's hopping to different locations on the x-axis. And the x-axis on the plots on the left represents different thresholds. So as you go further to the right, the threshold becomes more harsh. So on the left, you're permitting all actions. On the right, you are not permitting any actions except the safest one. And the top plot shows the reward, which in this case is how well you reach the goal. And the bottom plot shows the failure rate. So these are not the same thing because you can avoid failure, but yet still fail to reach the goal. So if you use a very low threshold, then the hopper falls all the time. So it has a high failure rate. If you use a very high threshold, then it basically stands still. It doesn't fall, but it doesn't reach the goal either. And if you choose a more intermediate threshold, then it will actually hop to the target. The blue curve is the LDM method. The orange curve is kind of the main baseline, which is the density constraint. And you can see that the density constraint does avoid unsafe actions once the constraint is very strong, but by then its ability to actually reach the goal is much worse. So we tested this across multiple different tasks, hopper, lunar lander, as well as a simulated medical task for a glucose for an insulin pump, some glucose. And in all these cases, we found that the LDM did a better job of avoiding catastrophic failures and also a better job of actually getting a higher return, which makes sense because if you get a catastrophic failure, then you don't succeed at the task. Okay, so the takeaways from this, Lyapunov density models can be trained via offline RL from prior data, and they provide a safety constraint that keeps downstream controllers inside the data distribution. In the same way that Lyapunov stability implies never exceeding a distance to the stationary point, the LDM implies never dropping below a desired density level. And this can provide in-distribution safety to downstream model-based controllers, as well as other kinds of controllers that I didn't talk about, like imitation learning and model-free methods. Okay, now let's talk a little bit more briefly maybe about task-specific methods for pre-training. So here's a big question. If you have prior data for the particular task that you want to solve, why is it not sufficient to just train on the prior data, right? For LDMs, we have prior data that was task-agnostic, but if we have prior data for the particular task we want, why can't we just train on that and solve the task? So what do we get from the online phase? Well, we can think of a Bayesian perspective on this question. We can say that, well, maybe if we have a data set, what we're really learning is a kind of posterior from the data set, a probability distribution over policies given the data set. So it's a kind of distribution over potential optimal policies. The data might not fully disambiguate exactly how to solve the task optimally, but it might narrow down our space of hypotheses. So if the uncertainty in this distribution is high, meaning that from looking at the data set, you think many policies might be optimal potentially, then you need to use this posterior to explore and adapt online to figure out which exact policy from that posterior is really the optimal one. So that's kind of interesting because it says that the role of this online adaptation is really to resolve leftover uncertainty that we might have from an ambiguous training set. And that's not really that profound of a statement because if your training set is empty, then of course you have full uncertainty and then you're just doing online RL. So there's a lot of uncertainty to resolve. If your prior data set is very large, you might have very little uncertainty to resolve. But nonetheless, we're going to take that perspective. When exploring online, try potentially optimal strategies and pick the best among those. So here's how we can think about this. We have prior data, and all of that prior data comes from some true MDP, right? That's where it came from. It came from an MDP, but we don't know what that true MDP is. And because the data set is limited, for that finite size data set, it might actually be compatible with many possible MDPs. So there is a distribution over possible MDPs, P of M given D, for which the data is compatible with all of them. So then a Bayesian objective for using this data would be to maximize the return of your policy in expectation under the distribution over MDPs that could be consistent with this data. That's a very Bayesian way to think about offline RL, essentially. So you can kind of you can imagine the process under which this policy is training as follows. You have a P of M given D, and you're imagining that at the first time step, one of the MDPs from this distribution will be sampled, and the policy will act in that MDP, but it doesn't know which one it's acting in, so it has to learn a behavior that will work well in all of them, weighted by their probability. The interesting thing is that at this point, this is actually a partially observed Markov decision process because the policy doesn't know which MDP it's in. So that's kind of an interesting statement that when you have finite data to learn from, you're actually trying to solve a POMDP, even though the real task might be an MDP. So the finiteness of your data actually induces partial observability because it induces uncertainty. Okay, so what could we do with this? Well, we could adopt a Bayes optimal strategy, which is to solve the epistemic POMDP, this POMDP where partial observability is induced by your limited knowledge, to get a policy. And then run that policy online. You can then minimize your regret when you do that, or you can even adapt it further. Now, the optimal POMDP solution in general is a memory-based strategy. So roughly speaking, the optimal solution in a POMDP would essentially be adaptive because it would look at its history, use that history to figure out which MDP it's in and change its behavior. So if you can somehow actually get the optimal policy for the POMDP, that policy will capture an adaptation procedure inside of itself. So that means that when you run it online, it will actually adapt. So pi is an adaptation or learning procedure if it is the optimal policy for the POMDP. Okay, that seems pretty great. Like we can just solve the POMDP and get a solution. Why is this hard? Well, solving POMDPs in general, much less from offline data, is actually a very difficult problem, much harder than solving MDPs. And furthermore, we don't even know what P of M given D is. We have to learn that from the data, and that's a much harder problem even than model-based RL. We're not learning one model, we're learning a distribution over models. So it would be really nice if we can sidestep these two difficult problems. It would be really nice if we could avoid having to represent a full MDP posterior, and it would be very nice if we could avoid having to solve complicated POMDPs. Okay, so let's try to avoid these things. So here's the first idea. The epistemic POMDP is not just any POMDP. It has some special structure. So when we solve the POMDP to get pi, the special structure will actually allow us to restrict the kinds of policies that we have to consider, and that'll be very convenient. We don't need an arbitrary memory. We only need to track the posterior belief over the MDP. So essentially, we have a prior belief, P of M given D, and as we collect more experience with our policy, that belief will change. So it'll be P of M given the union of D and the online experience. And if we assume that we're adapting within a single trajectory, it's really P of M given D combined with all the time step we've seen so far for the current trajectory. And we're going to call that belief B, and subscript T because it changes with every time step. So B is just some vector of numbers that represents your belief over which MDP you're in. The optimal POMDP policy pi is Markovian given B. So if you have B, you don't need any other memory. So we really only need two things. We need to be able to represent and estimate B, and we need to be able to train a policy condition on B so that it's optimal for all possible Bs. But this policy no longer needs memory. All it needs is B. So we're going to learn the policy with offline RL using random Bs, and then we'll represent and estimate B. That's still hard, so that's what we're going to talk about next. So what are these beliefs? Well, in general, the beliefs need to parameterize our belief, our distribution over MDPs. The interesting thing here is that a posterior over Q functions actually captures the posterior over MDPs. Like everything you need to know about the MDP is actually captured inside the Q function. So two MDPs are different in a relevant way only if they lead to different Q functions. If they don't lead to different Q functions, those differences are irrelevant to your policy. So that means that if B is sufficient to capture the distribution over Q functions induced by the MDP, that's actually all you need. And that's a really significant change because now we don't need to represent distributions over dynamics or rewards. All we need to do is represent distributions over Q functions, and that will be sufficient. So we need to represent P of Q given D, and we need to update it each time step to get an updated posterior over Q. The way we're going to represent a distribution over Q functions is by using a bootstrapped ensemble. Now, that's a very coarse approximation. It's basically saying I'm going to approximate the distribution over Q with a mixture of Dirac delta functions. But it's a very simple way to build the approximation because training bootstrapped ensembles for Q functions is a very well-studied topic. So essentially the way you do it is you just resample your data set and train independent neural net value functions on each resampled data set. And then the way we're going to update our belief is by changing the weights on the ensemble members. So instead of just averaging over the ensemble members, we'll do a weighted average, and the weights will represent our belief. So essentially, the member of the ensemble that seems to be agreeing most with what we're seeing will get higher weights, the others will get lower weights, and will adapt. So now B is just a vector of numbers, one number for every member of the ensemble that represents the weight on that member of the ensemble. So that's pretty convenient. Now B is a fairly small vector. If you have 16 models in your ensemble, B is just a vector with 16 numbers. Okay, now there are a few important details in instantiating this. One of them is that the Q function actually also depends on B. So you need to actually feed B into your Q function because even though each member of the ensemble is separate, they're not just estimating the optimal behavior for themselves, they're estimating the optimal behavior for any belief. That's a little subtle. Like your policy needs to get B as input, and each of your ensemble members also needs to get the B as input because the optimal behavior will change depending on your beliefs. So the ensembles are all updated on their own targets, but for beliefs that might say that other targets are actually correct. So during offline training, the Q function depends on B, and B actually changes each time step because at test time we will be updating it. So we have some dynamics on B. So to train, for every sampled mini batch, we're going to pick B randomly, and then we're going to update to B prime according to belief dynamics. So the belief has dynamics, which means that every time you observe a transition, B changes. And there's actually a little bit of a design choice in deciding what those dynamics should be. But formally what they should be is this: B prime should be proportional to B times the probability of the observed transition given the corresponding value function. So what likelihood do we use for this probability? Well, a very natural choice is to use the Bellman error as a log probability, which is basically saying that your values are normally distributed or distributed according to a Laplace distribution in this case with the mode given by the value function itself. This is actually a choice. So this is not the only choice you can make, but it's a very reasonable choice. It's just saying that the transition has high probability under your value function if the value function has low Bellman error for that transition. And then you can use this to induce dynamics using the equation in the lower line. So it's essentially using Bellman error as a kind of pseudo likelihood. So this is the full algorithm pseudocode. I'm not going to go through it in detail. It's essentially what I said before, but the important steps are during value function training, we sampled the current B randomly, compute the next B prime according to these dynamics, and then optimize with any offline RL method. And then we get a policy and a Q function that are both conditioned on B, and then we run the policy at test time, updating B according to these same belief dynamics as we go, which gradually narrows down your belief over the MDP over the course of a trial. So this method works. It outperforms, albeit somewhat narrowly, prior methods, including methods based on ensembles on some benchmark tasks. And in particular, the performance of the adaptive policy shown as a dotted blue line here at the top is significantly better than the performance of any one member of the ensemble. So the curved line, each of those points is a different member of the ensemble sorted from best to worst. And you can see that the adaptive strategy is actually better than the best ensemble member, which means that if we're adapting the belief, we're doing better than just picking one of the Q functions. We constructed a toy task that is meant to specifically elicit adaptive strategies. So here there's essentially an image classification task embedded inside an MDP where you get a picture from CFAR of a boat, a plane, a car, or something else, and you have to go to a corresponding door. So if you misclassified the picture, you get to change your mind and try a different door. But of course, that's never the optimal strategy for any single MDP, so you need to be aware of your epistemic belief to solve this. And that actually ends up working very well with this strategy. Okay, so I'm running about out of time, so I'll conclude. The key takeaways: training on offline data implicitly induces partial observability, which provides for a principal motivation for online adaptation. We can represent a posterior over Q functions with an ensemble and condition the policy on the belief. And future work could improve on this further by developing better methods to represent the posterior and maybe better methods to adapt. Okay, so I talked about how we can use prior data to provide some degree of safety. I'd like to thank all of you for listening. I'd like to thank the students that carried out this research. And if we have a few questions, if you have a few minutes, we can take questions.
Thank you very much for the talk. So maybe we can start with some questions from the panelists, maybe organizers.
Yeah, I just have a question, Professor. So in the definition of the Lyapunov functions and the Bellman equations, the task was defined as an infinite horizon and for the continuing tasks. And I wonder that if the task is a finite horizon episodic task, what is the final constraint that we need to put on the G function? And it can be any arbitrary one or...
Yeah, thank you. That's a good question. I actually swept under the rug this difference, but let me go back to the result here. So in the paper, we actually derived this for both finite and infinite horizons. And in the bound, actually, the analysis I'm presenting here is actually for a finite horizon. That's why there's this K final. And the only boundary condition is that you need the density model to have bounded error on the last time step as well, and that's epsilon fin. Now, typically, you'd expect that epsilon fin to be the same as epsilon p, but it's handled separately for exactly the reason you stated. We can also have a discounted infinite horizon formulation. That's a little bit more complex to write out, but it works more or less exactly as you'd expect. The horizon turns into 1 over 1 minus gamma, and that derivation is in the paper.
Okay, thank you. Yeah.
Do we have some other questions from the audience, from the other panelists? So maybe one question from me. I'm not sure if it's really aligning, but in terms of like sim-to-real transfer or continual learning, where there is explicitly like a distributional shift from the training and the testing, or the task itself can change over time, or the distribution, do you see that like this kind of methods can handle this distributional shift, or you want to identify the distributional shift and then just say that you cannot operate anymore in some specific task where the shift is too big? I think Professor Levin's here.
Sorry about that. I had a connection hiccup. Could you repeat your question?
So in terms of sim-to-real or continual learning, where we assume that there will be a distributional shift from what you have trained on and what you test on, do you see these methods can handle the situation, or more here the purpose is to identify this shift? And for example, if you want to induce safe behavior, just to stop acting in such situations.
Got it. That's a good question. I think that for the LDM method that I described, it's probably not a good fit for that, because it makes the assumption that you can avoid distributional shift, meaning that you start in some state that's pretty familiar, and then all you have to do is avoid going into unfamiliar places. But with a transfer learning thing like simulation to real world transfer, you would start off potentially in an unfamiliar situation right away. So you need there to be something gradual. And in particular, the LDM framework is not really accounting for changes in the transition dynamics. It assumes that you're still in the same MDP and you just need to avoid certain states. I think if you want to do something like what you're describing, I think you would need to combine LDMs with some additional mechanism for measuring epistemic uncertainty. You're basically measuring that things aren't working the same way that they worked before, even though you're in a similar state. And that would be an additional mechanism.
Yeah, thank you. Do we have other questions?
Yeah, I have a question as well. So I was wondering about the prior data. Is it normally, how difficult is it to acquire these data? And what if, about some applications like helicopter flight that normally we cannot get them from anyone? How difficult is it in those cases?
Yeah, that's a great question. I think it's very dependent on your domain, of course. So in some domains, maybe you can get a person to provide some training data if a person knows how to do the task. In some cases, you could also use data from past experiments. So maybe it's difficult to get a system that satisfies all of your constraints right away, but if you have to get started somewhere, maybe you have a few trials where there's some failures and you'd like to just have fewer failures later on. So it's domain dependent. In many cases in robotics, we can actually get data from human operators to get the process started. But in other cases, like for example, for a lot of industrial processes and operations research type problems, maybe there's prior data from some hand-designed control system that could be used to bootstrap the process.
Thank you.
Okay, I have a question from guest, and slide page 26 said MDP had a corresponding code. What if the data in this MDP is collected from a different policy?
Yeah. So the Q function can be trained on data from any policy. So you can have a Q function for a particular objective for a particular policy. And since Q functions like fit a Q iteration and Q learning are off policy algorithms, they can be trained on data that came from different policies. You have to be a little careful to make sure that, again, you account for distributional shift when you do that. And modern offline RL methods do have mechanisms for taking care of that. But other than that, that's not really a problem.
Okay, thanks.
Okay, thank you very much. I think that's all the questions, and we're running out of time. So I think now we can continue with the next speaker. Thank you.